Um, so which do you prefer, the old kind or the new kind?
The new one. Okay.
Whoa!
Thank you.
Okay, well, we're going to be talking about some of the technical issues of spinors, spin 1/2 fields, and today, and so there are going to be some indices. I think basically that each individual step is a simple matter, but there are a lot of steps. It's kind of like the Wallouz Trail. Okay, first of all, are there any questions? The TA pointed out that I forgot to put in a mass term for muon in the homework, so I added it. I'm going to review very briefly the Van der Waerden's notation, this business of dotted and undotted indices. I've never been a fan of this notation, and so I don't think you should pay much attention to it, but it does crop up in a much later chapter, something like chapter 27 or 28. Van der Waerden, by the way, was lived from 1903 to 1996 as a Dutch mathematical physicist. All right, in this notation, you can write the left-handed spinors as an undotted index and the right-handed spinors as a dotted index, and Schwartz adds a tilde. If we look at the left-handed ones, or if we just look at part of the Majorana mass, remember it was psi transpose sigma 2 psi, and this is minus I psi 1 psi 2 minus psi 2 psi 1, where here we're talking about psi being just psi 1 psi 2 like that. And of course, because the spinors anti-commute, this isn't zero. This would be zero if it were bosons. Now, what people like to do is to rewrite this as I psi alpha epsilon alpha beta psi beta, where epsilon is just the epsilon 1, 2 is 1, and that's minus epsilon 2, 1. So this is this is like the Levi-Civitas tensor, but in 2 dimensions instead of 3, or for that matter, 4. Epsilon as a matrix is minus I sigma 2. Is that thing is minus I, and then you have 0, I minus I 0 as the Pauli matrix. A couple of rules are that epsilon alpha beta epsilon beta gamma is sigma 2 squared, and this is equal to 1, or equivalently it's equal to delta gamma alpha. And I think what one is, let's actually work this out, because I don't remember what we're saying for this. So this is, suppose alpha's 1. So this is 1, this has to be a 2. So this has to be a 2 and a 1. And now this is, I'm getting minus 1 instead of 1.
because it's minus sigma 2 squared.
Yeah.
What's that?
Epsilon alpha beta, epsilon beta gamma, it's minus sigma 2 squared because of the I.
Oh, thank you. Brilliant. Because of the I, of course. Yes, so minus, minus. So this tells us then that we're getting minus 1, and if instead we did epsilon 2, 1, epsilon 1, 2, again we get minus 1. Okay, so in other words, epsilon 1, 2 is equal to 1, and that's equal to minus epsilon 2, 1. So the epsilon, whether the epsilons are down or up, or whether the indices are down or up, doesn't matter. Want one of each? You did. All right. Okay, now, some notation. Again, I'm not really terribly, I don't think this is terribly important, but just to go through it, we can write psi upper alpha as epsilon alpha beta psi beta, and then the chi lower alpha can be written as epsilon alpha beta chi beta. And now this is minus epsilon beta alpha beta psi beta chi gamma. Whoops, this is alpha gamma. And now we use this trick to say this is minus delta beta gamma psi beta chi gamma, which is minus psi beta chi beta. On the other hand, these things anti-commute, so this is also chi beta psi beta. And so what you see is that this notation has the advantage that if the spin is anti-commute, then this structure here is effectively abelian. Okay, now there's a definition then. Psi chi is then defined to be psi alpha chi alpha. So after we've gone through the trouble of showing the thing to be, we're now changing what we mean by this in a, well, it's actually probably the same thing. Anyway, this is then psi alpha epsilon alpha beta chi beta, and since the spin is anti-commute, it's minus chi beta epsilon alpha beta psi alpha, and that is chi beta epsilon beta alpha psi alpha, and so this is chi beta psi beta, and this is by definition chi psi. So in this notation, these things commute, and not suppressing the minus signs means you can do certain manipulations more easily. All of this was for left-handed. Now right-handed. I'm trying.
Thank you.
For right-handed, what we do is we use this twiddle, and we say that this is by definition alpha dot. So alpha dot again just goes from 1 to 2, but it's something that moves under the 0, 1 rather than the 1 0 1/2 rather than the 1/2 0 transformation. Since they anti-commute, this is chi tilde alpha dot psi tilde alpha dot with a minus sign, sorry, and that's minus chi tilde beta dot epsilon All right, hold it, this thing is going off the rails here. All right, okay, this is right so far. Now, the next step in my notes does not look quite right. It's, if we're going to make that a beta dot, and to make this an alpha dot, we want beta dot, alpha dot like that, and then psi tilde alpha dot. And we want to keep the chi on the left. So this is, I've got it exactly differently from my notes. Let's see. One. The bottom line is that this is the same thing as chi tilde psi tilde, but all right, this is actually alpha dot, it's actually alpha dot beta dot, so when you okay, it should look like that. And now we can flip the sign here. Chi tilde beta dot epsilon beta dot alpha dot psi tilde alpha dot, and that then is chi tilde beta dot psi tilde beta dot, and that's what this is by definition. Okay, so if one is careful, this all works out, but as I said, I think this dotted notation is, apart from, between the tilde and the dots, you've got two LaTeX nightmares. So I don't think we should go on too much about that, although I do have another page of notes here. Now, sigma mu, of course, is 1 sigma, and sigma bar mu is 1 minus sigma. And the kinetic part of the Dirac Lagrangian is I psi bar d slash psi, which is I psi dagger. This is two-component notation, so this is psi dagger. If this is left-handed, let me make that explicit, then this is sigma bar mu d mu psi. This is Lorentz invariant. And then the other part having to do with chi, with the right-handed part is chi dagger sigma mu d mu chi tilde. So this is something I went through probably a week ago. Now, in terms, once again, of these dotted and undotted indices, this the second term is chi tilde dagger sigma mu chi tilde. So that's chi tilde dagger alpha sigma alpha mu alpha dot chi tilde alpha dot. And Schwartz actually goes so far as to make this as a definition that the adjoint cancels the tilde, and so what we've got here is chi alpha psi alpha alpha dot mu pi tilde alpha dot. And in a sense, that sort of makes sense because this one started out, this thing is right-handed. When you complex conjugate a right-handed spinor, you've effectively got something that's left-handed. That's why writing it that way is not so crazy, but it is a bit bizarre. Going back to the left-handed one, we have psi dagger sigma bar mu psi, and so this is psi dagger alpha dot sigma bar mu alpha dot alpha psi alpha, and now by fiat we say, well, complex conjugating a left-handed spinor gives us a right-handed spinor, so we're going to call that psi tilde alpha dot sigma mu bar alpha dot alpha psi alpha. I don't know, this is kind of cute. There are a couple of useful identities. I will just write them down, although I did work through if you want to see one a verification for somebody else, I'll do it, but I don't think you do. So, I mean, these dots here really don't mean anything, do they? Because, I mean, it's just the same business. This notation is, I think, I think it's overkill. It's too cute. But people doing supersymmetry like it, and it's even had some application even in QCD. All right, well, I'll leave it at this point. Any questions? I think I should have skipped. All right, the next topic, I'm going to do some manipulation here, and I think what I'm going to say is that there's a typo in the book. Schwartz is stressing these equations, and so I'm not certain who's right. So let me just go through my derivation, and then and in this derivation there'll be some useful Dirac algebra. So following your advice, I'll just say some Dirac algebra. There was a story when I was a graduate student. There was a story that somebody was passing through Columbia, and he saw T.D. Lee sitting at his desk doing some calculations. He said, "What are you working on?" And Lee said he was just practicing Dirac algebra. So that leads me to show you some of this. The kinetic part, well, let us say the fermionic part of the Lagrangian for QED is, or Dirac's equation for QED is simply this. And of course, what this actually means is let me use it, d mu plus I E A mu minus n, gamma mu, sorry, minus m psi is 0. Okay, so this is the Dirac equation, and you remember last time if you multiply from the left by d mu plus I E A mu with an I, you get a nice equation that I will repeat here. I d mu minus E A mu, I d mu minus E A mu minus E over 2 F mu nu sigma, well, F lower mu nu, sigma mu nu, and then minus m squared psi. So I'm sorry about the crowding. Okay. And now what I want to do is I want to take the Hermitian conjugate of this equation. And so what we get then is psi dagger. And then these other things, what happens? Well, I goes to minus I, but then we have a minus, minus, minus I, minus, so we can just make everything plus. So what we get then is I d mu plus E a mu, I d mu plus E a mu. So you see what we're talking about is we're sneaking up on charge conjugation. Okay, there's that. So I Hermitian adjointed that part. Then the next thing is minus E over 2. F mu nu is simply real. So this is then sigma mu nu adjoint, and then minus m squared equals 0. Okay. Now, let me remind you what sigma mu nu is. Sigma mu nu is I over 2 gamma mu gamma nu. And this is also 2 S mu nu, so S, which is also 2 J mu nu. So when you make the Clifford algebra of the Lorentz group out of gamma matrices, the J mu nu are I over 4 gamma nu commutator, and the sigma mu nu is twice that, so it's I over 2. That's the sigma mu nu for here. We have to take the adjoint. Now, sigma mu nu adjoint is, of course, minus I over 2 gamma nu adjoint, gamma mu adjoint. And we can simplify that a bit by saying I over 2 gamma mu adjoint, gamma nu adjoint. Okay? All right. Remember, watch me like a hawk during these steps, because as I say, I've got a minus sign relative to the text. Okay. Now, let's remember what these gamma matrices are. Gamma mu, we can write it as 0 sigma mu bar 0. And by that, what's meant is, another way of writing it, I think, is this way. Gamma is equal to, now I'm using 4-vector notation, the 0 4-vector, 1 comma sigma, 1 comma minus sigma, 0 4-vector. That's another way of writing the 4 gamma matrices. Now, gamma 0, of course, is just 0, 1, 1, 0, where this 1 is a 2 by 2 identity. So obviously, gamma 0 dagger is gamma 0. Gamma 0 is Hermitian. On the other hand, the other ones are anti-Hermitian, because the Pauli matrices are Hermitian, but then transposition switches the plus sigma with the minus sigma, switches. Didn't quite get all the high frequency in there. They said switches instead of switches. Anyhow, the point is that gamma I adjoint minus gamma I. All right. And of course, as you know, whenever one talks about gamma matrices, I is the 4x4 identity, and 8 is the metric of space-time in whatever metric you're using. Okay, now let's play with these gamma matrices a little bit. Gamma 0, gamma I, gamma 0. What is this? Well, this anti-commutes. So this is minus gamma I, gamma 0 squared. Gamma 0 squared is plus 1 in Schwarz's metric. So that's minus gamma I, which is also gamma I adjoint. So, in effect, gamma 0 around a gamma 0 on both sides gives you an adjoint. And then if you adjoint that equation, remembering that gamma 0 is a Hermitian adjoint, you have this rule equals gamma I. So putting gamma 0s on both sides of a gamma adjoint undoes the adjoint. The next is that gamma 0 adjoint gamma 0. Well, of course, this is just gamma 0, gamma 0, gamma 0, because gamma 0 is Hermitian. Two gamma 0s make 1, and so this is gamma 0. So in general, then, we have gamma 0, gamma mu adjoint gamma 0 is gamma mu. All right. Now we can come back to this thing that occurs when we adjoint the whole equation. Namely, we have a sigma mu adjoint there. But before I do that, what I want to do is I want to take advantage of the fact that gamma 0 squared is 1, so I'm going to put in gamma 0 squared here. And in fact, psi bar, by definition, is psi dagger gamma 0. Okay? And so I'm going to stick in a gamma 0 squared there, and if we have an equation, something equals 0, we can always multiply both sides by gamma 2 from the right. Gamma 0 from the right. So this new equation then is psi bar gamma 0, or equivalently psi dagger gamma 0 squared. The rest of that, which was I d mu plus E a mu, I d mu plus E a mu. And now what we have is minus E over 2 F mu nu sigma mu nu dagger, because all I've done here is stick in the minus m squared gamma 0 equals 0. Okay. So I've just taken this equation and, this equation, and put in gamma 0 squared and multiply from the right by gamma 0. Okay. Now, let's see what gamma 0 sigma mu nu adjoint gamma 0 is. Well, this is gamma 0, I over 2 gamma mu adjoint, gamma nu adjoint, gamma 0, and this then is I over 2 gamma 0, gamma mu adjoint, gamma 0, gamma 0, gamma nu adjoint, gamma 0. And then, using this relation, we see this is just simply I over 2 gamma mu, gamma nu. Too many Greek letters, I know. And this is then just sigma mu. Okay. So in other words, we pull this gamma 0 through, and the only time it makes any difference is when it hits this. Otherwise, it just gives us 1. And the rule then is that this is just sigma, gamma mu, sigma mu nu adjoint, gamma 0 is just sigma mu nu. So the new equation then is psi bar I d mu plus E A mu, I D upper mu plus E A upper mu, minus E over 2 F mu nu, sigma mu nu, minus n squared, and then we can, well, there's no more gamma 0, it came through. And so that's the equation. So this differs from Schwartz by a minus sign in the F mu nu term. And I don't know. I think this is the correct sign. But if any of you think Schwartz has the right sign, send me an email and we can go from there. Now, under Lorentz transformations, as you know, the 4-vector psi transforms as e to the 1/2, and then up here we have I theta minus beta dot sigma 0, 0, I theta plus beta dot sigma. So that's an exponential of a 4x4 matrix. Effectively, it's the same thing as psi prime is e to the what did I call it? Let's see. I think I said minus z dot sigma 0, 0, e to the z star dot sigma psi. That's another way of writing it. Okay, now, something about gamma 5. Gamma 5, by definition, is I, gamma 0, gamma 1, gamma 2, gamma 3. So it's the product of all 4 gamma matrices. And it satisfies a very nice relation. It's a pity we didn't call this. Or let me also call it gamma 4, since we didn't have any gamma 4. Okay? Then, what you have is gamma mu, gamma nu, or let me say gamma A, gamma B, is 2 eta AB I, where I is the 5 by 5, no, it's 4 by 4, sorry. 4 by 4 identity. A and B go from 0 to 4. So eta is the flat space metric of a space with 4 space dimensions and 1 time dimension. And that's the anti-commutator. So in other words, gamma 5 squared is minus 1 yes. I don't see it here written as minus 1, but it is. No, I've got 1 there. Pity. Well, the way Weinberg does it, Weinberg arranges for gamma 5 squared to be plus 1, but then he has the metric where all the space indices are positive. I think we better stick with Schwartz, in which case we don't have this very nice relationship. I guess we might have, if gamma 5 squared really is plus 1, apparently it is, then this is a 5, in Schwartz's metric, it's a 5, and Schwartz's definition of gamma 5, of course you could take the I off there, but if we stay with Schwartz's notation, this then is a flat space metric for a space with 2 time dimensions and 3 space dimensions. And I think it's a lot of fun to talk about physics with 2 time dimensions. I've not spent much time doing it, but I found it very amusing anytime I did do it. And I encourage you to, it's better than CNN, let's say that. So sometime when you've got nothing to do, think about what physics would be like with 2 time and 3 space dimensions.
Actually, there are gravity theories with that property for gravitation.
Good. I'm glad to hear it. Anyway, it's amusing. All right, so let's see where we are here. This psi, I'm going to use a somewhat abbreviated notation. Remember, this is the 2-component left-handed, the 1/2 0. This is the 2-component right-handed, the 0 1/2 representation. And this gamma 5 actually, in this notation, so let me not call it gamma 4 because it turns out to be -1 0 0 1. And there are cute things that one does with it. Namely, a projection operator on the right-handed spinors is then 1 plus gamma 5 over 2. And this is 0 0 0 1, where each of these is a 2 by 2 matrix. Similarly, PL is 1 minus gamma 5 over 2, and this is 1 0 0 1, 0. Okay. And so P right on LR is 0 right, and P left on LR is left 0. So it's just a projection operator. Like any projection operators, you can verify. For example, P left squared is 1. Why is that? Well, it's 1/4 times 1 squared, which is 1, plus gamma 5 squared, which is 1, and then minus 2 gamma 5. And so this is just P left itself. So I said it was 1, it's not 1. The projection operator squared is the projection operator itself. Trouble with the neurotransmitters there. So gamma 5 squared is 1, and in particular gamma 5 anti-commutes with all the 4 gamma matrices. All right. Now the equations. Oh, the clock is still screwed up. The equations. The Dirac's equation then is this. It's minus m I sigma mu du. This is without electromagnetism. I sigma bar mu du minus m on, let us say left right because it's easier to write. And this is the same thing as I d mu gamma mu minus m on left right. And let me just refresh, explain why this is the case. The minus m is clear, but then the gammas are, this is basically I d dot, and remember this is the sigma mu, so this is 1 comma sigma, and this is I d on 1 comma minus sigma, and so that gives the minus sigma is the sigma bar there. So, and of course, all of this is 0. And now, if we take psi as being e to the minus I px, or e to the minus I p mu x mu, then carrying out the differentiation, what happens is du brings down minus I p mu, minus I times I is plus 1, and so what we get here is minus m sigma mu p mu sigma bar mu p mu minus m LR, but now in Fourier space. And if we split this up, what we see this is equal to is minus m e minus sigma dot p because of Schwarz's metric. Here it's e plus sigma dot p, and then minus m, and then LR equals 0. Okay. And another way of thinking about that is sigma mu p mu on R is e minus sigma dot p 3 vector on R is equal to m L. And so, and then the other equation is sigma bar mu p mu on left is e plus sigma dot p left, and that's equal to m right. Okay. So what you see is that the mass term mixes mixes the left with the right. You might wonder why that is the case if you remember back to the way I was writing the left-handed action. It would have been something like this: sigma bar mu d mu c, and then there was a c dagger. But then there was a term something like minus I over 2m, and then it was something like c transpose sigma 2c, and then I guess, no, it's a minus because of that I. Minus c dagger sigma 2 c star. Oh, this is transpose, of course, not dagger. And so what you might say here is, gee, this mass term doesn't seem to mix the one with the other. But in fact it does, because, well, I dropped the chalk, so it's a little hard to talk. But the equation of motion here then is something like this: I sigma bar mu d mu c equals some, or let us say plus I over, I'm leaving out a factor, I'm not being accurate to a factor of 2, but it would be then sigma 2 c star. In other words, if we differentiate this with equals 0, if we differentiate this with respect to c dagger, we get d mu c, and then we get a c star here. But remember, sigma 2 c star. Remember, if c is left, then sigma 2 c star is right. So this is mixing left and right, even with an ionic case. Right. Any questions? Okay, now, as I pointed out when I was doing this last week, in the case m equals 0, this equation is, for example, E R is sigma dot P R. And that is saying that sigma dot p hat, this is for the massless case, so E and P are the same. This then says sigma dot p on R is equal to R. And if we divide by 2, then it's a half R. So this means you have positive velocity for right-handed, and on the other hand, from this part, you would have sigma dot p hat over 2 left is minus a half left, setting in equals 0 in this equation. And so So what happens is you have the right and left-handed fields, when they're massless, they create particles of definite helicity. And this is true of any spin. It's also true for the photon, of course, is either has positive or negative helicity always, or a linear combination, but it's positive or negative. And the graviton also, although it's spin 2, it's either 2 units of angular momentum in the direction of motion, or 2 units of angular momentum opposite the direction of motion. And the same thing for the gravitino if it's massless, but nobody knows whether it's massless or massless. Okay. Any questions? I think there's another Schwartzian minus sign here. There certainly is at least one in the book, and I think he corrected the wrong one. But, you know, as I said, I was writing up the notes today, but then I had to run to the dentist. So I haven't. I'm going to write this somewhat differently because, I don't know, Schwartz somehow thinks that it makes everybody feel warm and fuzzy if you drop the operators out and just have the field equations. But, I don't know, it doesn't make me feel warm and fuzzy. I find it confusing. So I'm going to write it this way. And this is the way he'll write it eventually. And could one of you who's got the book, could you flip back to the spin 0 field and make sure I've got these signs right? Because I'm disagreeing with Schwartz for the signs here. But I think this is the right way to do it. So just spin 0 or the photon for that matter. Is this right, or do I have it backwards? All right. Okay, now of course, when we do this DQP, we're on shell if we're talking about real creation and annihilation operators, we're talking about real things that make real particles or stop real particles. And P0, of course, is therefore square root of m squared plus P vector squared. And what we want to do is learn something about what U and V are. These are called spinors. This annihilates the particle. This creates the antiparticle of momentum P and spin S. And of course, we're talking about spin 1/2, so it's going to be plus or minus. And now we've got this, the U is effectively left and right together, and so we've got this expression here, and we can think about that as P dot sigma if we want. So this is yet another way of writing the Dirac equation in momentum space. P dot sigma, and this is P dot sigma bar, again minus m, on U of P and S it should be 0. Okay, and but V has to satisfy this also. Oh, yes. Let's do the, you see, I use the minus I px to do the differentiation here to get these values. Over here, I'm having plus I p dot x, and so the thing is going to switch. So P is going to go to minus P here. So this is minus m minus P dot sigma minus P dot sigma bar minus m on V of P and S equals 0. So these are the equations that one wants to satisfy.
What you have there matches 13.2. What he has in spin 0.
Let me see 13. Yeah, good. Thank you. So I don't know. He was sort of floating away from the, I mean, he thought he'd make things simple by leaving out the creation annihilation operators, but I think it just actually just makes it. Okay, now let's go to the mass, to the rest frame of the particle. In the rest frame, what we have is minus m, 0, no, not minus m, 0, because this is just m, and that's just 1. So this is minus m, m, and in fact, if we divide by m, we just have minus 1. So minus 1, 1, I should follow my notes, but I'm talking too much. And then over here, what we have is minus 1, minus 1, minus 1, minus 1, v of 0 and s equals 0. And I find it convenient to sometimes take p to mean the 3 momentum and sometimes take it to mean the 4 momentum. And so just let us, so I'm gonna, it's just useful that a little sloppiness makes it easier, I think, to talk about these things. And we can write u of 0s as some, now remember, that's a 4 vector, well, it's a 4 component spinor, and so we can write it as alpha, in fact, we can write it as alpha of s, and why is that? Well, where these are each 2 component spinors. And why is that? Well, obviously, when you act on, in other words, if you act with minus 1, 1, 1, minus 1 on alpha, alpha, what you get is 0, 0, and that's what you want. You get minus alpha plus alpha. Okay, this is a 4 component equation, really. And on the other hand, for V, you want it to be, I'm using alpha and beta because he used the Greek letters that I associated with left and right. And, so let's just call this beta. And then what you need here is a minus sign. Why is that true? Because this is effectively 1, 1, 1, 1, and so you need beta minus beta. And here, alpha and beta are quite arbitrary at this stage. Weinberg, by the way, goes through this in a constructive way. The trouble, Weinberg's book is, of course, marvelous. It's the gold standard. The trouble is, there are so many steps. But if something confuses you at some point, the best way to get it straight is to read Weinberg. Now we're going to go, so we found out what the spinors are in the momentum 0 frame, but what one does is instead of using things with this generality, what makes more sense, and for the whole story, as I said, look at Weinberg, it's this, 1, 0, 1, 0. So this is spin up in the rest frame, and we're talking about positive mass at the moment. Spin down, again, rest frame. V of 0 plus minus 1, 0, 1, 0, and V 0 minus 0, 1, 0, 1. Okay, so of course you remember the trick I showed you last time or the time before that you take any 4-component spinor, any 4-component field that satisfies the Klein-Gordon equation, multiply it by ID slash plus m, and that gives you a solution to the Dirac equation. And so that's another way of constructing these. Maybe I should have done that. Maybe I'll flash apply you next time. Okay, in the momentum in the actual momentum frame, and we're going to be going in the z direction. You know, state law says that you've got to have the z direction up, and it's everything's simpler in the z direction. So, what is p dot sigma? Well, it is, and now this is a 2 by 2 matrix. This is E minus P 0, 0, E plus P. This is because it's P here is E 0, 0, P. Okay, and P is PZ, but I'm leaving off the subscript Z. And P dot sigma bar is the same thing, but you flip the sigmas, the spatial sigmas, and so this is E plus P, 0, 0, E minus P. Okay. And so what do we have now? Well, Schwartz lets A equals square root of E minus P, B equals square root of E plus P, and M squared turns out to be cos E minus P times E plus P, because that's just E squared minus P squared, and this is the same thing as A squared P squared. All right, with all this notation, then what do we have as a Dirac equation? So what is Dirac's equation for the U spinors, particle spinors as opposed to the anti-particle spinors? It's minus M P dot sigma bar minus M. By the way, I put a new homework assignment on the web page over the weekend. It's to do part B of 10 point something, 10.5 maybe. Part B is, I think, pretty simple and instructive. And then to do 11.1, which is some gamma matrix practice. And part A of that 10.5, or whatever it is, it's not true that the action density is invariant. What happens is the action density changes by a total derivative, which doesn't affect the equations of motion, and you can integrate it to a surface term, but it's not zero. Okay, so what is this on U of P and sigma? So now this is a 4 by 4 U of P and S. This then is a diagonal matrix minus AB minus AB minus AB minus AB, and then some off-diagonal pieces so it looks like this, and this minus it. All right. U of P and S. And it turns out that the answers then are the following. U of P and S you can set equal to A0, 0B, B0, 0A on what we called alpha of S earlier. And of course our alpha S were 1, 0, 1, 0 or 0, 1, 0, 1. Those are the alphas of choice. And see where, okay, And so this turns out to be square root of e minus p, 0, 0, square root of e plus p, alpha s, and then square root of e plus p, square root e minus p. And the v's, v of p and s turns out to be something somewhat similar, namely square root of e minus p, 0, 0, square root of e plus p, beta of s, minus square root of e plus p, 0, 0, minus square root of e minus p, beta of s. And the both are minus signs, okay. All right, now, all right, I ran out of, time here. All right, let's see. Going again to the case where you have spin up and pin down in motion in the z direction, then what you've got finally is u of p and let us say plus, then square root of e minus p, 0, square root of e plus p, 0, and then u of pz again down is 0 square root of e minus p, 0 square root of e plus p. And then the v's are v of p plus is square root of e minus p, 0, minus square root of e plus p, 0, and v of p minus is 0 square root of e minus p, 0 minus square root of e plus p. All right, so these are the natural spinors, or these are the ones that one uses conventionally. And if you're talking about spins in a different direction, basically, you basically subject these to a rotation, and you then get something that's more complicated. Now, there are certain identities, and there's some more algebra. I apologize for writing all this down. It's kind of tedious. Okay, first of all, u bar of p and s, u of p and s prime. And what do we have? Well, this of course is u dagger of p and s, gamma 0 u of p and s prime. And this would then be, well, I skipped something here that I thought was basically, let's see. Square root of p dot sigma. Okay, what's that? Well, this is, again, we're talking about motion in the z direction. So this is e minus p 0, 0 square root of e plus p. So this is a cute way of writing that. And one can also write square root of p dot sigma bar, and that's square explain that in a little more detail. Let's look at this one. Then, first of all, P dot sigma here is E minus P dot spatial sigma, but now we're in the z direction, and so P is equal to z hat P, length of P. And so this thing, in that case, P dot sigma is E, and then sigma is only sigma 3 because P is in the z direction, so this is minus P 0, 0, E plus P, okay? And now if you have a diagonal matrix, you can take its square root very easily. You can just say square root of P dot sigma is square root of E minus P 0, 0, square root of E plus P. And so that's what we've got. And now, using our recipes for the spinors, what we get is square root of P dot sigma, this, well, he called it C, I was calling it alpha. Square root of P dot sigma bar alpha, and then the whole thing dagger on 0, 1, 1, 0, that's gamma 0, and then square root of P dot sigma. And now this is an alpha prime for a different spin. P dot sigma bar alpha prime. And so what is this? Well, this is effectively alpha dagger, and then square root of P dot sigma, square root of P dot sigma, and then this C dot sigma bar, I should say, and now the gamma 0 inverts them, and so we have square root of P dot sigma bar, square root of P dot sigma, and then alpha prime. And now, so this is, it's alpha dagger, well, alpha star actually, since I've already transposed it. But now this is square root of P dot sigma bar, square root of P dot sigma bar, P dot sigma, and then alpha prime. And now what's P dot sigma bar? Well, this is P0 minus sigma dot P, P0 plus sigma dot P. And if it's in the z direction, then it's, well, actually, no matter what direction it is, it's just P0 squared minus P squared, and so that's just M squared. So this thing gets us to M, and then it's alpha star, or alpha dagger alpha, since the alphas are the same. And then there are two of them, so it's 2M alpha dagger alpha. And if we choose the alphas to be not in some arbitrary direction, but to be up or down, in other words, we're talking about motion in the z direction and spin in the z direction or the anti-z direction, then this would be delta SS prime. So we can make them orthogonal. If we make them orthogonal, then we get that. The similar relation for the V's is V bar of P and S. V of P and S prime is minus 2M delta SS prime. Again, thinking of S and S prime as being strictly up or down. And you'll be happy to know that something is 0. V bar of P and S, U of P and S prime is 0, as is, of course, U bar of P and S, V of P and S prime. So these are 0. And while we're at it, U dagger of P and S, U of P and S prime is, let me just skip to the answer, it's 2 delta S, S prime, again, thinking of the spin as up or down rather than in an arbitrary direction. And there's a similar relation to the V's. V dagger of P and S, V of P and S prime is 2E delta S, S prime also. Okay, we're almost out of time. Maybe I have time for one more relation. I think I will write these 2 relations down because they're quite nice relations. And they're ones that are almost a little bit mystical almost. So a sum, S equals 1, 2, up and down, in other words. U of P and S, U bar of P and S is P slash plus M. Well, isn't that a cute expression? P slash being P mu gamma mu, with one index up, one index down. And the sum, S equals 1 to 2, V of P and S, V bar of P and S is P slash minus M. So those are quite nice expressions, I think. And they're used a lot in, we'll start next time at more or less this position. And what I may show you is the way I think about some of these things, if I can compactify it so that it doesn't take more than maybe 10 minutes. In other words, I think that trick would get us to these spinors much more quickly than this long roundabout. But since Schwartz was doing it, I have to say. Also, I had to go to the dentist. We didn't have enough time. All right, let's turn the thing off. Any questions?